All right. Again, I'm just going to have the recording on to record the screen. Well, this screen really, it's not that screen. So today the plan is going through two examples on linear equations, and then maybe when we have time, we're going to look at exact equations. Do you have any questions or comments before we begin? Just in case I forget, there's a homework 2 posted. It's due the 13th at 10 p.m. I think, or sometime there. Double check. I would say that take a look at the questions. You don't have to do the problems fully, but at least know what kind of questions is on it. And if there's any particular questions that you read it and then you think about it, you don't know how to begin, just bring it to recitation on Thursday. Okay. All right. Any other things? I guess another thing I want to mention is that there's a link for the Zoom link for my office hours and also for recitation. Only for my recitation. If you have to attend lecture or go to someone else's recitation, use a different link. It's not the same Zoom link, just in case. Because I got some notification last Friday when you guys had the lecture remotely, which I hope it didn't cause any issues there. But anyway. All right, so let's begin with the first example here on linear equations. Which is ty prime plus 2y equals t squared minus t plus 1 with the initial condition. Y of 1 equals 1/2. We're just going to solve this initial value problem. So a problem like this is a linear equation, right? Because we get, well, after we divide by t, we get y prime, and then we get some function times y. So if we have, just recall that if we have y prime plus p of x y equals f of x, we can use integrating factor r of x. So we basically multiply the whole equation by r of x, and then solve for r at some point, plug it back in, solve for y. So the first thing we have to do is we have to make sure we begin with y prime, right? Nothing in front of the y. So we have to divide by t, so we got y prime plus 2 over ty equals, divide by t on the right hand side, so that's a t minus 1 plus 1 over t. So that we end up with y prime to begin with. And the sum term was y. And this 2 over t is what we call p of t or p of x in general case. So the next step is a very important step. We multiply by r of t. So I'm just going to write r there, but note that when I see r, I really means that r of t, a function of t. So multiply by r of t, so we get ry prime plus r times 2 over ty equals r times t minus 1 plus 1 over t. And I'm going to rewrite this equation. On the left-hand side, I'm going to leave it as ry prime plus r prime times y. The other side, the right-hand side, stays the same, so r times t minus 1 plus 1 over t. The left-hand side, I can rewrite it as r times y derivative equals the right-hand side. Because the left-hand side was basically part of the product rule, right? We just rewrite it using product rule. All right, we can stop there because we don't know r there, so we can't really solve. But from the second to the last equation I had, we can figure out that the derivative of r is equal to r times 2 over t, which is equivalent to the dr dt equals r times 2 over t. We can solve for r from here by using separation of variables. Or you can just use a formula which is given. The formula is the integrating factor r of x is always equal to e, base e. In the exponent we have integral p of x dx. In this case, p of x is equivalent to 2 over t. And then we can use the shortcut. R of t is equal to base e. In the exponent we have integral 2 over t dt. It works all the time if you choose to memorize it, but again, I don't, because I just get confused when I memorize too much. So you can just figure out what the r of t is directly and then put it here. But what I do is I use separation of variables. It's kind of long way to get it, but it works. Both way works. So in my way, I'm going to move the r to the left. Look at 1 over r dr equals 2 over t dt. Integrate both sides. We get natural log absolute value of r equals 2 natural log absolute value of t. There's a c there, but you don't need to add the c. Add a base e, so we get r equals e to the natural log absolute value of t. That's a 2 in front of it. You don't want to take this put in there, right? Because that's exponential terms. It's complicated. It's get messy. Not really complicated. Just get messy. So I can simplify this. Last time what I did is I switched the order of 2 and the natural log. So I put 2 behind natural log. So e to the natural log absolute value of t times 2. And don't worry about that 2 in the exponent, because this part we can focus on first. So that's e to the natural log of something. We get the absolute value of t out of there. So we get absolute value of t squared. Because of the 2 is still there. This 2 is the same as this 2. It just stays in the exponent. And that's the same as t squared. If you integrate directly from there, you should end up with the same thing. It's faster that way, but it's the same. Any questions? Now we're going to take r, put it back into that equation. So we get t squared y derivative equals t squared t minus 1 plus 1 over t. We can simplify the right-hand side by distributing t squared. We can integrate both sides to get rid of the derivative. I'm going to do both at the same time. So we get t squared y on the left when I integrate. The right side I have to integral, distribute t squared, so we get t cubed minus t squared plus t dt. Every term there you can integrate using power rule. So that's a t to the 4th over 4 plus minus t cubed over 3 plus t squared over 2. Don't forget to add a constant c. And then the very last step is divide by t squared to solve for y. So y, if we divide by t squared, y equals t squared over 4 minus t over 3 plus 1/2 plus c over t squared. This is the general solution with the constant c. So if you think about it, the first couple of steps is multiply by r and then rewrite the equation in this form. The second step, or maybe not really the second step, something on the side, is that you have to figure out what the integrating factor r of t is, right? You can just find it directly, or you go through the longer way I did. And then you plug it back in, and then integrate one more time. then basically solve for y after that. Any questions on this work? It's, I have to say though, that solving differential equations is a very technical work. You just kind of have to, there's certain procedures that you follow, and if you are careful, this is really not too bad. You just have to be careful not like misplace a negative or make mistakes. And then remember that we have an initial condition for this, y of 1 equals half. If we want to find the c, we're just going to use that initial condition. And this means t equals 1, y equals half. You plug this initial condition into this equation. That should give us a c equals 1 over 12. I'm not going to do that work. Don't forget to take the c, put back in there at the end. Any questions on that? Are you feeling a little bit okay with this method? If not, definitely do more problems in the book to practice. All right. Any questions? Final call? All right. So here's the second example if you don't have questions. The problem is solved, again, just like the previous one, we solved this initial value problem. 2y prime minus y equals 4 sine 3t. With initial condition, y of 0 equals 13 over 37. So I'm going to give you a couple of minutes to solve this on your own. And then I'll stop writing the steps I have for you to compare. I'm going to write down what I have. You can continue to work on your own work. So feel free to compare with what I have. Okay, so this is what I have. Do you get the same thing? More or less. So I get I equals e to the negative 1/2 t. And in this part I have r times y prime equals 2r sine 3t. So I put it there, you substitute for r there. So the next step is to integrate. So I get e to the negative 1/2 ty times y equals integral 2 times whatever the rest, but I'm going to bring 2 outside. So I get e to the minus 1/2 t sine 3t dt. And we have to do a little bit more heavy lifting to figure out what this integral is. But question for you, which technique do we use to integrate that? Like how do we find this integral which we do use? Not U substitution. Right, what's the next technique that's as good as U? Integration by parts? Perhaps? Well, let's try with integration by parts, right? Let's just focus on only this integral. Don't worry about anything else. Just look at that. So to integrate this, we're going to use integration by parts. So I'm going to say I'm going to call u equals sine 3t. It really doesn't make a difference here which one is u. You can call the exponential part to be u. Doesn't matter. du equals sine, give me cosine 3t times 3 dt. And then dv will be the exponential part. And then we can find v from there. I want to show you, this is what I do to find the v. So first thing I'm going to integrate this, obviously, right? So when I integrate exponential function, I get itself, but be careful with the coefficient. So if I integrate directly, I get e to the negative 1/2 t. That should be part of the answer. But what is the number in front of it? Or is there anything else I need to add? So what I do is I check. So if suppose I have this as my v, and I differentiate this, what do I get? If I differentiate the v, let me use a different color and I'll erase it. If I differentiate this, I'm going to get e to the negative 1/2 t using chain rule times another negative half, right? But that's not what I want. I want to have 1 times e to the negative t. So it looks like I have an extra negative half that I don't want. So that means I have to multiply something here to get rid of the negative half, to make it positive 1. So the part that I need is I need to get rid of this negative 1/2. I have to multiply by something, so I'm going to multiply by negative 2. That way I get positive 1 out of there. So now if I check dv, if I take the derivative of v, I get negative 2 times e to the negative 1/2 t. But then in the exponent, I get another negative 1/2. So now I have negative 2 times negative 1/2 will cancel, give me positive 1, which is this part. That's kind of like a quick way to use the U substitution. So on the side, not the work I already had, like a few lines done. On the side, I'm going to write down the integral. So integral e to the negative 1/2 t sine 3t dt. That's equal to, using integration by parts, this is u times v, so that's a negative 2 e to the negative 1/2 t sine 3t minus integral v du, so that's a negative 2 e to the negative 1/2 t times positive 3 cosine 3t dt. So it looks like it didn't really help us much. We went from a integral of exponential sine becomes an exponential cosine. Right, it doesn't help us, but at least it looks like we're going from sine to cosine. Maybe if we use integration by parts again, we go back to sine. Oh yeah. Oh yeah. I can, if you send me an email later, I can either send you the note or send you the link to the video recording. That way. Yeah, no problem. But it's okay to take picture, no problem at all. I apologize if I move a little bit too fast. Tell me to, just let me know, I'll slow down. But does that kind of make sense, the first step using integration by parts? And then what I'm going to do is I'm going to basically repeat the same process with this integral here. But the first thing I'm going to do is I'm going to move that -2 and a 3 in front of it. So this -2, I'm going to put it in front of it. So that goes away. And then this 3, I'm also going to move in front of it. So that's -6 in front of this negative sign becomes -6, +6 there. And then the remaining part of the integral, I'm going to use integration by parts again. So I'm going to say u equals cosine 3t, du equals negative sine 3t times 3 dt, and then we still have dv to be the same, and the v is the same, the e to the -1/2 t dt, and then -2 e to the -1/2 t dt. No, -1/2 t. And if I put using the integration by parts correctly for this integral here, I'm going to end up with, I'm being a little bit lazy not writing down everything, just writing down the second integral here. So that's going to be -2 e to the -1/2 t cosine 3t minus 6 integral e to the -1/2 t sine 3t dt. And if I rewrite this, if I put this chunk in this part and then multiply with +6, right, that's a minus a -6. So multiply by +6, let me just write down that line. So I get integral e to the -1/2 t sine 3t dt is equal to -2 e to the -1/2 t sine 3t, the first term doesn't change. But then I have +6, right, minus -6 is +6 times this bracket. So I get +6 times -2, that's a -12, e to the 1/2 t cosine 3t. +6 times -6, that's minus 36, integral e to the -1/2 t sine 3t dt. Well, you probably think we still have the integral here that didn't go away. But the beauty of this sine and the cosine is that you begin with e to the -1/2 t sine 3t dt. And then after double integration by parts, you still have it inside the right-hand side. Which means, well, if it's some unknown, something we're looking for in there twice, that means we can combine them, move them to the same side. We can actually combine this part with this part on the left and then solve for it. So this part, along with the -36, we can combine with this integral. We don't know what it is, but we can solve for it. So if I move it to the left, add it to the one already there, so I get 37 integral e to the -1/2 t sine 3t dt. And on the right-hand side, I still have two terms I did not touch. I'm being lazy here. I don't want to write down everything. I hope you can forgive me on that. So this part I highlighted, I didn't touch it. So I'm going to just leave it the way it is. Kind of move it right down here. So that stays right there. Is that okay? Just being lazy here. And then remember we're solving for the integral, right? So the next step is just divide by 37. I'll write down what I have. So divide by 37, the integral e to the negative 1/2 t sine 3t dt is equal to everything divided by 37, so I get negative 2 over 37 e to the negative 1/2 t sine 3t minus 12 over 37 e to the negative 1/2 t cosine 3t. You probably wonder, can we factor out a e to the negative 1/2 t? Absolutely, if that's what you want to do, to make it easier to write. So that's the integral we're looking for, right? Remember that in the previous, I'll scroll this up. Remember that in the previous step we were looking for this integral. Well, now we found it. And before I make a mistake, so don't forget we also have to add a constant c. That's what I forgot. Because this is the indefinite integral. I should probably add a constant c above, but it's okay. So now we're just going to take this chunk, this right-hand side, and substitute into the previous step we didn't finish. So is it okay if I move up a little bit? All right, so if I take what I had and put into this part I underlined, like put it here, I have the left side is e to the negative 1/2 t times y. The right side I have 2 times whatever I'm going to put there, right? So that's going to be 2 times everything goes there. And I'm going to distribute the 2, so that becomes, when I distribute the 2, I get negative 4 over 37 e to the negative 1/2 t sine, sorry, that's a negative 1/2 t sine 3t, and then minus 24 over 37 e to the negative 1/2 t cosine 3t, and the plus c times 2. But you don't have to write c times c, you can just write c1. Call it a new constant. Or you can just use a c, as long as you know that this c is different from the c we had below in the integral. We're almost done here. So the next is just solve for y, right? We have e to the negative 1/2 t. We don't need it, so divide that term. So we're going to divide by e to the negative 1/2 t to both sides of the equation. And the benefit is that, the good thing is that we already have a couple e to the negative 1/2 t on the right-hand side, so that cancels nicely. So we got y equals negative 4 over 37 sine 3t minus 24 over 37 cosine 3t, and then plus c1 divided by e to the negative 1/2 t, right? But because we divide by a negative exponent in the exponential part, it becomes a product. So multiply by e to the positive 1/2 t. So that's the general solution. And then now we need it looks long, but it's actually not that bad when you plug in the initial condition. So now if we use initial condition, y of 0 equals 13 over 37. I think that's a good number to put in there. It's really nice when we put 0 for t, right? Because sine of 0 is 0, cosine of 0 is 1, e to the 0 is 1. So you really don't have to worry about sine and cosine on the exponential part. You just deal with C1, negative 24 over 37, and then y. It turns out very nice. I guess that's another thing I want to mention is that, when you work with initial conditions, at least when you do it by hand, they usually end up to be, reasonable. It's not like something too complicated that you can't calculate by hand. Any questions? Well, if you don't have questions, I want to go over one example on exact differential equations. I know that Professor Gibson started with one example in lecture. He probably didn't finish. That's what I heard. But so let me go through another example just to help you practice this technique. So exact equations. So suppose, well, before I keep writing, any questions about the previous example or the one before that? No? All right, so suppose we have a differential equation that we can write in the form of the first chunk is just some expression involving x and y that doesn't have derivative attached to it. The second part has the another expression with x and a y in it, but it has the derivative attached to it. And the right-hand side equals 0. Suppose you have an equation that you can write like this. And if there's a continuous function, let's call it psi. It depends on x and y. So this is a PSI psi. Suppose we have some function psi, and suppose it's also true that the derivative of psi with respect to x, psi x, equals this expression m we have. So whatever that is, that's just the derivative of psi with respect to x. And the derivative of psi with respect to y is equivalent to n. Suppose those are all true. And suppose we have, well, if psi is continuous, if it is continuous, then we definitely know that psi, partial derivative psi x, y, means that we take the derivative of psi with respect to x first, and then we take the derivative of whatever we have with respect to y after that. It must equal to psi yx. Just means that we take the derivative with respect to y first, and then with respect to x. This we can rewrite it as, because psi x is what m is, right? So that's an m. So this basically means dm dy. The psi y is n, so that's a dn dx. So basically we want this to be true. If that's true, then this has to be true, because this part is m, so psi x, y is just my. Psi y x is just nx, so that's n. So suppose we have this function psi, and then we just say those are true, and then this equation, this relationship is true as well. If that's all true, then the differential equation given is exact. That's what we call exact equation. Okay, what's the benefit of the equation being exact? The benefit is that the solution to the differential equation we know immediately it's going to be psi xy equals a constant c. So if we know the equation is exact, we can end up with those two relationships, and we also know this equality is true. And then we also know the solution. What does the solution look like? So this is a very compact notation if you're not familiar with it. But let me highlight the steps, and I'll use the example. So the first step you want to do, you want to look at the equation, make sure that it begins with a 0 on the right-hand side, and then you begin with a positive sign between the m part and the n dy dx part. So those are the two things to watch out for. The first step is going to be figure out what the m and n is, or psi x, psi y. The second step, you want to check whether the equation is exact. The third step is that you're going to solve for psi x and y. To solve for it, we're going to use the equation in step 1 when we list the psi x and the psi y. So using psi x equals m, psi y equals n. So that's step 3. Step 4, you're just going to write down the solution by adding a c to the other side. That's how we find the solution to the differential equation. So, any questions before I give you an example? I think the example probably helps a lot. So here's the example. Suppose I have 2xy squared plus 4 equals 2 times 3 minus x squared y times y prime with initial condition. Don't worry about the initial condition until very end. So we're going to solve this. So after you write down the question, you take a look. So, well, we don't have a 0 on the right-hand side, right? And we don't have doesn't look like this might be the m because it doesn't have the derivative. Okay, so that's the m. But then we don't have m plus n and the derivative. So we need to move this over and make it positive. So the first step is move the right-hand side to the left. So that's a 2xy squared plus 4. Minus 2 times 3 minus x squared y prime equals 0. So at least we got 0 there on the right hand side. But like I said, the part that multiplied by the derivative that looks like it's the n. Okay, so that's the n. The one that doesn't have the derivative looks like that's the m, but it's not addition. We have to make sure that's a positive between them. So let's get rid of the negative sign by distributing it into the parentheses. So I get 2xy squared plus 4 plus 2 times, you can distribute the negative 2 altogether, it doesn't really make a difference. Well, it's probably, I don't know, for now it's fine. Negative 3, because we move the negative inside, so negative 3 plus x squared y times y prime equals 0. Now if you look at it, here we have this part doesn't have the derivative, so that's the m. Then you have positive, but then you have this part times the derivative, so this is the m, this is the n, and then 0 on the other side. So now I'm going to say, I'm just going to list them out. So psi x d psi dx, I'm going to call that m, which is equal to 2xy squared plus 4. And I also have d psi dy, I'm going to call that n, which is equal to 2 times negative 3 plus x squared y. I'm going to distribute the 2, so that's a negative 6 plus 2x squared y. So that's the first step. Figure out what those two expressions are. Any questions? The next step is is to check whether that equation is exact, right? If it's not an exact equation, we're not going to find the solution this way. So the step 2, check if differential equation is exact. So we want to make sure that psi xy equals psi yx. You don't have to write this down in the future if you don't like to. You can just write down my equals nx. That's what we want. Well, we don't have my, so let's find it. So my means we take the m expression, take the derivative with respect to y. Now, when we take the derivative with respect to y, all the x has to be treated as constants, just like the numbers. So, on the side, I'm going to write my is equal to, just take the derivative, so that will be 2x as a constant, y squared give me 2y, and the 4 give me a 0. So that's going to be 4xy. And then n sub x, the derivative of n with respect to x, the 6 will become a 0, the 2 is a constant, x squared will be 2x, y doesn't depend on x for now. You kind of treat it as its own variable, even though y depends on x as the equation, but it's not here. So the y is to be treated as a constant, so that's going to be 0 from negative 6 plus 2 times 2x times y stays. So we get 4xy. So that's a good thing because both are the same. Questions? So we do have this, right? That's what we wanted. So we have my equals nx. That tells us that differential equation is exact. That's a good thing because we know what the solution looks like. So solution to the differential equation is going to be psi xy equals a constant. We need to know what psi is, but at least we know what the solution looks like. Any questions before I move on? This is the first 2 steps. All right, I'm not hearing any questions. So step 3, let's find psi. How do we find it? Well, the only thing we know about psi is that we know the 2 derivatives, right? We know that psi x equals this, psi y equals this. Let's begin with one of them. I'm going to begin with the first one. It doesn't really matter which one you begin with, as long as you can integrate it. So we know that psi x equals 2xy squared plus 4. You don't have to write the m there. You could. It's not necessary. We can integrate. Yep.
When you start from, how do you know which one is m and which one is n?
Excellent point. So the way I remember it is that the n is the one that doesn't have the derivative multiplied with it. N is the one that you multiply the derivative with. So you have to make sure it's 0 on this side and addition between those 2 terms. So what I did with that problem is that I make it 0 here, right? So I move this term to the left. Then I'm looking at it. The derivative is multiplied with this. So that's probably the n. This 2, the 4, and then this doesn't have derivative, so that's probably going to be all together, this m. But then I have to make sure it's positive between what I think is the m and what I think is the n, by moving the negative into the n. That's a very good question. It's kind of, you look at it, okay, there are 2 terms basically. With derivative, that will be the n. Without derivative, that's the n. Great. So from here, what I'm going to do is I'm going to integrate with respect to x. So if I integrate with respect to x, the left side I get psi. The right side I get integral 2x y squared plus 4 dx. That's going to be, I'm taking a few more steps. So that's the integral 2x y squared dx plus integral 4 dx. I'm sure you all have, you know what the second one is. But be careful with the first one. When we integrate this with respect to x, we have to treat the y squared just like we should treat it as a constant. So the y squared don't get involved when you integrate with respect to x. So that's going to give me 2x. When we integrate it, give me x squared. Y squared is just a coefficient basically. Plus 4x plus a constant. Be very careful with this constant term. So this constant term, let me write it down. So constant, it's only constant in the sense that it doesn't depend on x. Because we integrate with respect to x, this constant doesn't depend on x. It's constant relative to x, but it could depend on y. We don't know. Could depend on y. It may not depend on y, but we don't know. But it could depend on y. It just doesn't depend on x. So that constant, instead of using a c, you can use c of y or h of y, doesn't matter, something, to show that it might depend on y. It just doesn't depend on x. Sorry, I might be 1 minute late. I hope that's okay. Let me try to go through this. Okay, so now we have psi equals x squared y squared plus 4x plus h of y, the constant term, not depending on x. How do we find this part? Well, we use psi of x, we have to use psi of y there, right? So, recall psi of y equals, I'm just going to copy it down, negative 6 plus 2x squared y. That's what I had, that's what n is. So what I could do, this is what I know from the equation, this is what I've done. I could take the derivative with respect to y and then try to match the terms. So from here, I'm going to find psi of y equals x squared stays when I take the derivative with respect to y times 2y plus 4x give me 0 plus the derivative of h of y with respect to y is just the derivative. Sorry. H of y, when I take the derivative with respect to y, this becomes h prime. And if I match this, the one I took the derivative and the one that we already know from very early on, if I look at the terms, those two match, those two should match, otherwise they're not going to be the same. It should be the same. So that will be h prime of y is going to equal to negative 6. And if we integrate this to find h of y equals integral negative 6 dy, that's going to equal to negative 6y plus a constant c. And it turns out that it's not necessary to keep the c. Eventually it cancels with another c in the equation. So you can call it c1 for now, it doesn't matter. So note that this is not necessary. I'm sorry, I'm almost done, I swear. So now we just put everything together. We know h of y. We can put in there. So we get psi equals x squared, y squared plus 4x plus h of y, which is negative 6y plus c1 is not necessary. Now we can write down the solution to the differential equation, which is just psi equals c. So that's going to be x squared, y squared plus 4x minus 6y equals some constant c. And then we have to use initial condition to find c. Use initial condition y of negative 1 equals 8 to find c. Sorry, that's it. Now, the reason I said this is not necessary because even if you have a C1 here, you have another C on this side, you can combine them to give you a new C. All right, sorry, 2 minutes late. I'll try to let you leave 2 minutes early next time.